Hi class, this is a second video on the Doppler effect and specifically how we use it in astronomy. And you'll remember in the previous video we discussed the Doppler effect, we discussed the equation, the Doppler shift equation right here. Lambda is the wavelength of the light that you observe here on Earth, so that would be either this light or this light depending on whether or not the source, and in general, we're always talking about stars when we're talking about the source of light. So whether the star is moving towards the observer or away from the observer, you either you'll observe this blue shifted light or this red shifted light. And lambda naught, which shows up twice in this equation, that's the wavelength that the light is actually emitted at. And we then address the question, if this is what you observe, lambda, how do you know what lambda naught is? You don't directly observe lambda naught, you directly observe lambda here on Earth, either the blue shifted or the red shifted light. The answer to that is that you look at the detailed spectrum of the star, and in the spectrum of all stars you see this characteristic absorption line spectrum. And in particular, you look at the sun. So here's the spectrum of the sun, and you see some really prominent absorption lines. You see this line right here, and this pair of lines right here, and you see other really prominent lines. And what we can do is we can really just, focus on some of the really prominent ones. So that's right here. So this would be like the spectrum of the sun, the unshifted spectrum. And the reason that we know that the sun is unshifted is because even though the Earth is orbiting around the sun is not moving towards us or away from us. When we look at the spectrum of the sun, we're looking at the unshifted spectrum of a star. And pretty much, roughly speaking, all stars have more or less the same pattern of absorption line. So any star you look at, you're going to pretty much see the same pattern. Now, in future chapters, we're going to correct this. We're going to see that mainly depending on the temperature of the star and also the chemical composition, some stars will have more prominent lines than others, but you're always, for the most part, going to see the same pattern of very prominent absorption lines. If you look at the spectrum of a star that's moving away from Earth, then you're going to notice the same pattern, and you can recognize the pattern just by, you got the triplet and the doublet and the singlet like here. So you identify the whole pattern, and then you see that the whole thing is shifted to the right. And it's shifted to the right because all of this light has been Doppler shifted, and it's been Doppler shifted in such a way that what we receive here on Earth in this spectrum is we observe longer wavelengths than what it's emitted at. And similarly, if the star is moving towards us, this whole pattern of absorption lines, it all gets shifted to shorter wavelength. And that's all in accordance with that equation that we used. So if you want to actually measure the speed of the star, what you want to do is you want to choose one of the absorption lines. So like in the example that I'm going to work through, we're going to choose this one, which is H alpha. So this is from hydrogen. You go back to the lessons on the Bohr model of the atom. You remember H alpha is that absorption line that shows up in hydrogen gas when the electron is bumped from its first excited state to its second excited state, and it absorbs, in doing that, it absorbs this 1.9 electron volt photon, and that has a wavelength of around 656 nanometers. That's that red absorption line in hydrogen, and that shows up more or less in all stars. So we're going to use that, and what you can do is the exact wavelength from either laboratory measurements or from looking at the spectrum of the sun. You know exactly the wavelength that H alpha should show up at. So if it shows up at a longer wavelength, you know the star's moving away from us. If it shows up at a shorter wavelength, you know the star's moving towards us. So here is an example problem pretty similar to what we have in our homework. This is the exact wavelength of H alpha right there, 656.281 nanometers. Here it is in the spectrum of this star right here. In this example problem for this star, when you very carefully look at the spectrum of this star, which is what this is right here, and unfortunately this has some kind of strange units. This is in angstroms. Angstroms an angstrom is a tenth of a nanometer. So just to put this in perspective, this 6,000 angstroms, that's equivalent to 600 nanometers. This 6,600 angstroms, this is 660 nanometers. So it makes sense that H alpha 656 is just a little bit to the left of that marking of 660 nanometers. Anyways, in the spectrum of this star, it's observed that this H alpha absorption line right here, it doesn't show up at the laboratory or the sun value. It shows up at a slightly longer wavelength, 656.323 instead of 281. The fact that the observed wavelength shows up at a longer wavelength than the emitted, what we know it's emitted, we can conclude that the star is moving away from us. And then what you do is we can take these two wavelengths and we can plug it into this equation. Before we plug it into the equation, what we can do is we can just do a tiny bit of algebra. We can just drag the speed of light onto this side of the equation, and then we will have solved for the velocity. So anyways, this is just a little bit of algebra between these two steps. So the velocity of the star is equal to the speed of light, which is 3 times 10 to the 8th meters per second, multiplied times all this stuff in the parentheses. And you want to evaluate all of this first, and then take that result and multiply it times the speed of light. So now we can just plug stuff in. So I do that right here. So we have lambda minus lambda naught. So first of all, let's just do what's in the parentheses. So lambda minus lambda naught, that's 656.323 minus the 656.281. And then we divide that by lambda naught. So here's what you get when you subtract those two wavelengths, and there's lambda naught. And then you plug this in your calculator. Notice the nanometer unit cancels out, so this just turns into a number. Your calculator tells you this is 0.000064, and then it'd be a good idea to convert this into scientific notation. We do that by moving the decimal place 5 spots to the right, and we form a number between 1 and 10, which is 6.4. And since we move the decimal 5 spots to the right, we're going to take that 6.4 and multiply it times 10 to the negative 5. 10 to the minus 5 is the same thing as 1 divided by 100,000. So this is 6.4 times 1 over 100,000, which is the same number. So that's the stuff in the parentheses. And then the final step is to multiply this number, because that's what all of this in the parentheses is. We need to multiply it times the speed of light. So that's what I do right here. So we take the speed of light, 3 times 10 to the 8th meters per second, and then we multiply it times that number. And to do this multiplication, you take 3.0 times 6.4, that's 19, round it to 19. Your calculator is going to give you more digits after that, but just round it to just to 19, two significant figures. And then you take care of the exponents. You have 10 to the 8 multiplied times 10 to the minus 5. So that's going to be 10 to the 8 minus 5. That's 8 plus negative 5, which is 3. So, and 10 to the 3 is 1,000. So 19 times 1,000 is 19,000 meters per second. So in this problem, just based on the observed wavelength and the wavelength that we know that that absorption line should show up at, we can conclude two things. The star is moving away from us because this number is larger than this number, and we get the actual speed of the star to be 19,000 meters per second. And this is a very similar problem to what's in the homework. In the homework, we use we don't use H alpha, we use some other absorption line. So this would be the laboratory wavelength. This would be lambda naught, is this 486.133. That's what it should show up at, but in the spectrum of the star, it shows up at 486.112. So it shows up at a shorter wavelength than what it's emitted at. So that's a clue right there. And then you follow the exact same steps as in the problem. So I hope that helps. This is a very important thing in astronomy, to be able to measure the speed of stars. This allows us to do things like discover exoplanets, planets around other stars, And among other things, it also is what enabled Edwin Hubble to discover the expansion of the universe, that all galaxies are moving away from Earth and our Milky Way galaxy, except for some very nearby galaxies. And this is what we now refer to as the Big Bang theory of the universe. We'll talk about this later in the semester.